Good morning. Our lecture today is about the second part of autocorrelation. But let's start with a quick review about what we did last time. What's meant by autocorrelation? Autocorrelation means successive error terms are correlated with each other. So in the model, y equals beta 1 plus beta 2 x2 plus u, we assume that error at time t and error at time t minus 1, there is no correlation between them. Or the expected value of ut minus 1 and ut equals 0. But if this assumption is violated, this means that there is an autocorrelation problem. It normally occurs in time series data. So autocorrelation means error last year may be a linear function of the year before, and so on. What are the main sources of autocorrelation? Number one, the nature of economic and business variables. As we said last time, that most economic and business variables tends to move together. This implies that observations of an economic variables are expected to be interdependent over time. Say, for example, consumption expenditure over time is expected to move during the period of recovery and slow down during the period of recession. And the error term may take the same pattern, may follow the same direction. Number two, variable transformation. In some econometric models, economists use the change form instead of the level form, or the first difference form instead of the level form. So instead of using, say for example, c equals c node plus c1 y1 yt plus ut, this is the consumption function, they are going to use the first difference form. Using equation number 2, may cause a problem of autocorrelation. Number 3, model misspecification. Say for example, that the model is a non-linear invariable model. Say for example, a consumption function c equals c node plus c1q plus c2q squared plus c3q cube plus u. And by mistake, we are going to use C equals C node plus C1Q plus U. So economists are going to use this one by mistake. The problem of autocorrelation will occur in this case. Number 4, the autoregression or lags. In some econometric models, we are going to use the lag of the independent variable as one of the explanatory variables. Say, for example, this is consumption function, C node plus C1 y plus C2 C t minus 1 plus ut. So this is the variable and this is the variable lag 1. Lag 1 means that you are going to depend on the last year value. Value in this year is going to depend on the last year value and so on. This is known as the random walk hypothesis. In this case, the problem of autocorrelation may be found. Number 5, non-stationarity variables. Non-stationary variables. Non-stationarity of variables usually occur using time series data. As when we are going to use a time series model, a time series data, the variables must be stationary. Stationary means that the mean and the variance do not change over time. But if you are going to use non-stationary variables, the error term will be autocorrelated with each other. How to detect the problem of autocorrelation? The most common test used in detection of autocorrelation is Durbin-Watson test. Or known as D statistic. D is calculated as summation ET minus ET minus 1 all squared divided by summation ET squared. Or in other words, sum of squared difference of residuals divided by sum of squared residuals. If the residuals are autocorrelated, they will be following an autoregressive scheme, which means that error at time t will be function of error at time t minus 1, or we can write the equation as ut equals rho ut minus 1 plus epsilon t. So now, how to detect the problem of autocorrelation? We are going to calculate Durbin-Watson or estimate Durbin-Watson using this formula. Actually, we are not going to calculate it. It's normally given by the statistical packages, EViews or even Excel, SPSS, anything. So with respect to you in the exam, it's going to be given for you the Watson value. And we have to compare it with the critical value. In case of Durbin-Watson, there are two different critical values. As we said, in F and T, there is only one critical value, but in case of Durbin-Watson, there is an upper limit and lower limit based on the number of observations and degrees of freedom. The value of Durbin-Watson varies from 0 to 4. And here is the lower limit and the upper limit. This is 4 minus the lower limit, and this is 4 minus the upper limit, and here is 2. As we said that the upper limit and lower limit can be found from the table, just like F table, there is a Durbin-Watson table. Okay, and we have to reject or accept the null hypothesis. With respect to H node means that there is no autocorrelation, and H1 there is autocorrelation. If the value is lower than the upper limit, so we are going to reject H node. And there is a positive autocorrelation. If it is from 4 minus the lower limit and 4, we are going to reject H node, and there is negative autocorrelation. From the upper limit to 4 minus upper limit, this is, in this case, we are not going to reject H node, or we are going to accept H node, and this means that there is no autocorrelation. If the value is between the lower limit and the upper limit, so this is inconclusive areas. This test couldn't help us in order to identify whether there is a problem of autocorrelation or not. Inconclusive. And also from 4 minus upper limit and 4 minus lower limit, this is also inconclusive. So let's take an example. Suppose that a regression equation was estimated for a sample of time series data where n equal 20 and k equal 3. And you found that the Durbin-Watson is 1.92. So this is the calculated value for Durbin-Watson. And if you know that, the upper limit and the lower limit are 0.98998, and with respect to the upper limit, it is 1.676. So this is our figure. This is 0, lower limit, upper limit, 4 minus lower limit, 4 minus upper limit so the value of Durbin-Watson is 1.92, which is located here. So this means that there is no problem of autocorrelation, or we are going to accept H node. Here is another example. This is the results for an estimated model. Y, standard errors, sorry, coefficients, standard errors, T's, key ratios, and R squared, Durbin-Watson. This is the upper limit and lower limit, and we would like to know whether there is a problem of autocorrelation or not. This is the lower limit, and this is the upper limit. 4 minus lower limit. And 4 minus the upper limit. So the value of Durbin-Watson is 1.56. So it's here in the inconclusive area. So we cannot determine whether there is a problem of autocorrelation or not in this case. Another example, y equal negative 194.79 plus 0.92 x squared, x2. So the lower limit is 1.5 and the upper limit is 1.59. 4 minus the lower limit is 2.5. And 4 minus the upper limit is 2.41. So Durbin-Watson is 1.22, which is here. which means that we are going to reject each node, and there is a positive autocorrelation. How to cure? Actually, you are not going to talk about how to cure in details. Just you have to know that e-views and any statistical package can help in order to solve the problem of autocorrelation. The most common used method is the first order autoregressive scheme, which means that you are going to add the lagged value of the dependent variable in the equation. If the true value, just to sum up كده, you have a number of questions. Number one, if the true value of if the true total cost function is C equals C naught plus C1Q plus C2Q Q squared plus C3Q3 Q to the power 3 plus U. And if instead the following is estimated: there will be a strong possibility to encounter the problem of heteroscedasticity, multicollinearity, autocorrelation, if this is an MCQ question, MCQ question, and it's required to find the which problem is there is a strong possibility to find this in this equation. So the problem of autocorrelation is the expected problem in this case. Another question: which of the following models may exhibit autocorrelation? A, Ct equals C naught plus C1y plus C2 Ct minus 1 plus U. B, Ct equals C naught plus C1 y t plus the ut. C, a change in Ct equals C naught plus C1 a change in yt plus U a change in ut. Finally, both A and B. So the correct answer in this case will be D. Another example: In the presence of autocorrelation, OLS estimators are unbiased. R squared will be overestimated. OLS estimators will be inefficient. The correct answer is all of these. Number 4, if the estimated value of Durbin-Watson statistic is 1.76 and from D table the critical value of D was n equal 50 and degrees of freedom equal 2, the upper limit is 1.63 and the lower limit is 1.46. According to this information, we have to know whether there is a problem of autocorrelation or not. Number A, can't reject the null hypothesis of autocorrelation. Number B, can reject the null hypothesis of autocorrelation. Number C, can conclude that there is a negative autocorrelation. And number D, can conclude that there is a positive autocorrelation. In this case, we have to identify 1.76 will be located in which area. So this is 0 and 4. Lower limit is 1.46. And 1.63 the upper limit. 4 minus the lower limit will be 2.54, and 4 minus the upper limit will be 2.37. The value is 1.76, which is located here. So we are not going to reject the null hypothesis of autocorrelation. So the correct answer is point number A. This is the end of our lecture today. Thank you and see you next week.